Modern applications are often containerized, making them more portable and efficient. As you scale your containerized applications to handle larger and larger workloads, managing the infrastructure can become rather complex. Fortunately, the open source and extensible platform Kubernetes can help manage containerized workloads across multiple host environments. By defining your Kubernetes environment in configuration files, often in an industry-standard YAML format, you can eliminate much of the manual work traditionally required for managing a distributed deployment. Examples of traditionally manual tasks that Kubernetes streamlines are load balancing traffic to your containers, orchestrating storage volumes, automating rollouts to new versions or rollbacks to previous versions of your application, and repairing the cluster if a portion of it crashes or goes offline. The array of features built into the Kubernetes platform makes it particularly ideal for cloud-native application environments requiring portability or rapid scaling. Environments are declared in configuration files, so they can be easily migrated or recreated on a different server or cloud provider, as long as Kubernetes is installed and ready. Let's look at some of the key components within Kubernetes that make up a cluster. At the core of the Kubernetes platform is a pod, the smallest deployable unit of computing. A pod is a group of one or more containers defined by a specification detailing how those containers will run. Containers within the same pod share network and storage resources. Think of the pod as a logical host for its containers. These pods run on nodes in your Kubernetes cluster. Nodes can be virtual or physical machines depending on what type of cluster you are using. Within every node in a Kubernetes cluster are a few common components. First, a node needs a container runtime responsible for running individual containers, for instance, Docker. Next, a kubelet agent ensures containers are running in pods as defined in your specifications. A node also has a kubeproxy network proxy that maintains networking rules and allows communications to and from your pods. Nodes essentially run the containerized components of your applications. In addition to nodes, a Kubernetes cluster has a control plane that serves as the central layer for managing nodes and pods in the cluster. Components in the control plane make global decisions about the cluster based on the definitions you provide. For example, if you've defined that 8 replicas of a given pod should be running in your cluster, and only 7 are running after one crashed, the control plane will start a new pod to satisfy your replica criteria, returning to a state of 8 running pods. All of these features combined make Kubernetes a cohesive, portable, extensible, and automated platform for managing your containerized applications with declarative configuration. For InterSystems Iris Data Platform users who build and run containerized applications, the InterSystems Kubernetes operator allows you to reap all of the benefits of Kubernetes and InterSystems Iris without extra manual work. The InterSystems Kubernetes operator extends the Kubernetes API with a custom resource that represents an InterSystems Iris topology. While this operator is not required to deploy InterSystems Iris within Kubernetes, it exposes information and settings in InterSystems Iris to Kubernetes for better streamlining and automation of application-specific tasks. For example, with the InterSystems Kubernetes operator, you can configure the data nodes in your cluster to be mirrored, or elastically scale your compute nodes to appropriately handle user workloads. Without the operator, you would have to manually interact with the individual containers running InterSystems Iris for tasks like these. To learn more about Kubernetes and all its benefits, you can browse the thorough documentation on the Kubernetes website. If you'd like to read more about the InterSystems Kubernetes operator, head to the InterSystems documentation site.